Two samples that we've been working on for a while now. They're called Rockstar and Rumstar for Recon's K and M star samples. And there are a lot of protagonists in the room who are leading this effort. I'm just here to be the showman. Many of you have this sticker in your hands right now. This is a summation of everything we know within 10 parsecs in the stellar population. We're not touching planets or brown dwarfs in this particular plot. This is coming out in a review article that Wei-Chun Zhao and I wrote. That's coming out effectively now. The galley proofs are in. And this summarizes by percentages how many of each type of star you have in the universe of this type. So basically, when I handed you a sticker, or one of the students handed you a sticker, we handed you the universe. This is the answer. And we've heard about the 10 parsec sample several times today. Celine and Ricky have done a nice job pulling together the stars and stuff. We're done. There are no stars missing. The number is 373 within 10 parsecs. I will bet you that it is good to within 1% and probably better than that. There's nothing hiding. We've got all the companions. We've got all the orbits of the binaries and stuff. So you put Gaia together and all that. And of course, what we care about in this room really today are the K and M dwarfs, because that's 86% of the sample. Those people who study the more massive stars, they don't matter. And extragalactic, nah. All right, so I always press students to say, what is your science question? Tell me what your science question is. And so I started writing them down and I gave up, because they're endless science questions and each one of you probably has your own, and you should put it into the spreadsheet for the conversation later. I'm just teeing it all up. We have two teams of students working on this. We have Team K and Team M. Leonardo and Hadari have graduated from the group. They're off building their careers. Sebastian and Tim are in the crowd. Serge, Jen, and Elliot are all still working on the sample with us. Jen and Elliot are in the crowd. And then Andrew, Aman, and Madison are the second wave of the M dwarf aficionados. And I would like everybody who's on this slide in the room to stand up now. And there's a reason for this, because when you ask me questions at the end, if they're easy, I will answer them. And if they're hard, I'm sending them the question. You can ask them all the questions you want after it's all over. And Wei-Chun and I just try to keep the gang going. You'll see more on that in a second. So the first thing you have to do is, what is a K star? What is an M star? We all have our own definitions. We put a tiger team together and we hammered on this for months. And the blood, sweat, and tears metaphor actually works here. There was definitely sweat. There were a few tears. There wasn't much blood. But we finally came up with a way we are defining K and M dwarfs. And we went through colors, we went through absolute magnitudes, we went through temperatures, we went through luminosities. It was all just really painful. And we decided that the best way to do it is an absolute G magnitude. So we decided on the line here at 5.5 that separates the G stars from the K stars. You go back to Richard Gray's comprehensive survey of nearby stars. He's an expert in getting spectral types around that range, and you can sort of run the dividing line between a handful above and a handful below that. And this schematic also is in Wei-Chun's in my paper, so you can pick it up there anytime now. Then we got to the K and M dwarfs borderline, and you can see that in the upper right panel there. And the red dots in that panel are M dwarfs by spectral type, either from Richard Gray or us, or Neil Reed and Suzanne Hawley and John Gizis. And the black dots are K stars. And so we just basically split the difference with a handful or so on each side of that. That's how we define 8.1. And then the universe offered us the easy one. I used to think this was hard, but now it's easy, right? So Serge Dietrich, back in the early 2010s, 2014, I think it was, before Gaia existed, did a clever thing. And he found where the minimum radius occurred, where the stars, as you remove mass, get smaller, but as you remove mass from brown dwarf, they get larger. And Serge spent his thesis determining the luminosities and temperatures and figured out from that famous equation we all know, L equals 4 pi r squared sigma t to the fourth, what the R was for the smallest star. And he pinned it at L2.5 spectral type. And in fact, the universe now has confirmed that, because there's a gap when the brown dwarfs hit there. If they're young, they keep sliding down because they don't last. They can't hold on to the luminosity. And so you start seeing a gap in a spray at the end of the main sequence. So that's where we drew the line at 17.8. That gives us the definitions of K and M that we're using. And Tim Johns is leading the effort for our Rockstar sample. We're going out to 50 parsecs. That's over 4,000 K dwarf systems. At this point, we're going big or going home. We're not going home yet, so we're going big. And so we've got almost, 5,000 systems 4,000 systems plus all the companions. It's going to be probably 6,000 stars, all said and done. And he's going to sweep through all the wide companions from Gaia and WDS and everything else that's been found. Madison LeBlanc is leading the effort for the M dwarfs. This is a little tougher in some ways because it goes much fainter and they're harder to pick up the companions and they have not been as well surveyed before. But the wide companions, of course, are all in Gaia out to 25 parsecs. It's more than 3,000 samples. So we're jumping out to a much larger horizon so that we can really ramp up the statistics on things like the luminosity function and mass function. My job is like our mascot for the group, Miles, our puppy, is to make sure the graduate students get fed. As long as you feed them, they will continue to do good work. Now, we all know what the purpose of this work is in this room, right? You want to know your neighbors, of course. You want to establish observing programs that are volume complete and volume limited. Both of those terms come into play here. And you want to get statistical samples. That's where we are now. Everybody can do the one-off and find a planet, but we want statistical samples to say how often does this happen in the universe? And we're going to provide these lists to you on the world. You can see the dates on there. I'm scaring the crap out of Tim and Madison right now because I put a 2024 on that, not a 2025, because everybody wants the lists. They're coming together very nicely. The thing that we do differently in recons that a lot of folks don't do is that we check every single dot and we vet them like crazy. And when I say the word vet to Miles, he gets a very strange look on his face. When I say the vet to the students, sometimes they get a strange look on their faces. All right, well, Miles is grown up now and we've collected all these marbles. What are we going to do with them? Here are just a few ideas. You have to characterize all the stars themselves. That means the populations of the luminosity and mass functions. That means determining if they're young and or active, how fast are they rotating, and whether or not they have long-term cycles. This is very different. You're going to see an example of all this stuff here in a second. Then you want to figure out the multiplicity, of course. As we've heard over and over again, the binaries matter. Zach, don't you dare ask me about binaries. You can ask me anytime. We've already had these conversations. There are wide binaries, of course. There are speckle binaries. Catherine gave a nice talk earlier today about speckle. Zach the first instead of Zach the second. Zach 1, Zach 2, they both work with Sebastian Lepine. That's how we keep them straight. Then we have RV surveys, of course, that Jose and others have talked about. We have orbits that Elliot Reimuth is working on. And then, of course, we have the planets that everybody's interested in. What will you do with these lists? This is what I'm curious to hear, especially in the breakout sessions. All right, are we complete? Yes, in a short answer. Here is the 50 parsec rockstar sample broken into 8 equal volume shells. That's why the numbers look funny on the bottom. Those are volumes. Other than people on Team Recons, if you can tell me what's happening in that next to last bin and why it's higher, I will buy you a drink. Hyades, who said it? Oh, Eric, you're cheating. I owe you a drink anyway. Yes. Those are the Hyades K dwarfs that have slipped in because they're at 47-ish parsecs, right? The M dwarfs are in good shape. I thought that maybe it was going to turn over near the end, but it doesn't. So we do have effectively complete samples. I like to use the word effectively because there are going to be a few slip-throughs. I didn't mention it, but in the sticker that you have there, if you tried to pull the statistics out for the sticker from Gaia, you would miss 8% of the systems in DR3. So you have to do other things like go to our own stash of parallaxes that we've got. So the Gaia is not going to be complete at the 25 parsecs, but it's going to be pretty well done. It's a few sort of percent kind of dearth that we've got going, and we'll probably pick those up in later data releases when they have more data to solve for the binaries. There's the HR diagram for the K-dwarfs, and this is the one I want to show because you can see all the companions there. Anything below the second line there in red is an M dwarf companion to a K dwarf. And so we're vetting and confirming all of these companions to these stars. And so you will know what they look like. This is the similar plot for the M dwarfs. You can see there's the hook there. And as Andrew Caparis pointed out, it looks like Italy. And the white dwarfs become the island. So they're effectively complete and they're 1,000 well-vetted systems. We use primarily these 2 telescopes in Chile, the SMARTS telescopes, the 1.5 meter, we've been doing RV surveys since 2017, and the imaging survey at the 0.9 meter for almost a quarter of a century now. Very quickly, little highlight for each of the students in the group. Sebastian Carrasco is leading this effort. You can see there on the left, the H alpha line. We very clearly measure that with a Chiron spectra with a resolution of 80,000. You can see lithium there. It's actually the bit on the left. You can see the shadowed sort of window there. Then we have the calcium triplet. One of the lines we get very well. We get both the triplet itself, the absorption feature, and the re-emission in the core. The quick takeaway, he's got a poster coming up, is that 10% of all K-dwarfs are young or active in the Rockstar sample. And we've got about 30% of them already surveyed. I think that number is actually closer to 40% when we push through the data that's not in his primary sample. This is the speckle survey for the K-dwarfs that I'm leading. Two different versions of the same plot. Along the horizontal axis is the separation. The vertical axis is just the number of stars. Simple histogram. The takeaway here, if you go to the linear scale on the bottom, the one I prefer because I think in linear space, that most stellar companions are within 5 AU. So you have to get the ones in close if you care about the exoplanet searches. This is Leonardo's graph of his radial velocity survey. Complicated and not enough time to go into it in super detail, but you have the orbital period on the horizontal axis, the RV semi-amplitude, and those lines cutting across. Above the top line is a star. From that line down to the brown dwarf line or brown dwarfs, and then below that are super Jupiters and exoplanets. And you can see that the blue dots were known, the green dots are ours, the gray dots are ours, and then the pink dots are smaller planets that we're not sensitive to with Chiron. But the bottom line here is that there are tons of discoveries just pouring out of this survey. And the key here is that if you look at HARPS, high-res, SB9, all the surveys that have been done, we've now passed them in the number of K-dwarfs within 50 parsecs surveyed for companions, including planets. We've got 350. Not gonna have time for that because Danielle's waving signs at me. Madison's work here is the luminosity function of the M dwarfs. You can see here the classic turnover that you get at some point, but that's not a good way to look at the M dwarfs. The primaries are in purple, the secondaries that are resolved are in blue, and the key, folks, are the white bits of the unresolved companions. So those are systems where we know there's more than one object, but we haven't seen the second object yet. We're working on that more in a second. If you take these into account carefully, you find out that the mass function is smooth, there are no kinks in it, and it's rising to the end of the main sequence through the M dwarfs. And effectively, we've surveyed all of these. Andrew Kaparis is working on twin stars. These are virtual identical twins in pairs, and the quick takeaway is the bottom right one, where you have one star in emission, one star in absorption. They're the same mass, the same color, the same age, the same composition. They were born together, they're in the same system, and yet one is in emission, one is in absorption. You can plot these using Chandra data and X-rays or just H alpha for us. The two boxes labeled N are that system where one is on one side of the spin down break and one is on the other side of the spin down break. But folks, everybody assumes if you look at a star, you can guess what its history was like, and these twins do not match. So we have a problem here. Anytime you say, I know the star, this is only a snapshot in time, and even in the snapshot in time, they do not match. So all that stuff you say, historically, I know what the star did, we don't. That's the bad news. Aman Carr is leading the effort on the TESS rotation, and he's got a breakthrough here. Top line is the raw data coming out of TESS. The green dotted line in the middle is the stuff you get from PDC-SAP when they give you the answer because they're looking for transits. This is a transiting system with a planet. And the curved red thing, that's the bit you get if you use something called unpopular, which he is probably now the world expert because the inventor seems to have gone off into extragalactic land. And he's now gotten to the point where he can determine a rotation period of 120 days using test data. And we are going to be able to do, using 13,000 light curves that he's already downloaded in the supercomputers, he's got 93% of all the M dwarfs within 25 parsecs. He's got the light curves. Long-term stuff we've done at the 0.9 meter, folks look at the horizontal axis. That's 25 years of data on these stars. I don't think there's any other database in the world that has this, and we can do cycles up to 30 years long with these stars, but we can't do very many of them because it's a very time-intensive effort. Elliot Weimut's leading the orbits, and this is a very special graph. These are from SOAR. They go from 2/3 of a year up to about 30 years. This is a long-term thing from the 0.9 meter, and a very important event happened at the red arrows. Remember, this is a long-term program. That's when Madison LeBlanc was born. And she's holding in her hand a finder chart at the telescope at the 0.9 meter in Chile that's older than she is. We can get periods up to 30 years for orbital stuff. Elliot's orbital work here, you can see the recons and source stuff really adds up. The two bits to take away from this are that the tidal circularization period is about 7 days for M dwarfs, and that there seems to be a gap of circular orbits beyond 10 years. We've got almost 200 orbits already. Finally, I'm almost there. This is a mock-up of where the planets have been found, where you've got the K dwarfs there between the orange lines and the M dwarfs to the right of that. And my question for you all is, what percentage of stars in these two samples, rock star and rum star, turns out it's the same number, have planets reported? Huh? No. Known planet, well, reported planets. How many? How many percent? 20? 10? 3. Bottom line, we have a lot of work to do, folks. All right, my summary slide is this one. It's just how much stuff do we need to do yet? If it's in green, we basically got it done. If it's in yellow, we're working hard on it, but we could use help. And if it's in red, everybody's desperate. Thank you. I'll take easy questions.
Well, Zach too was working for asking questions. Am I allowed to ask questions?
I suppose.
So we saw in Jen's talk earlier about she's able to now get the two-brain diagram for the M stars. Do that with the Ks. So how many?
Oh, sure. Hadari actually did that in the first pass for his sample for his thesis, and it turns out of his 601 halo.
Very much. I'm so sorry we have to cut this short. If you have more questions for Todd, we'll be around the poster.
I'll be around.
All right. You can also ask questions to any of the speakers on Slack. So, keep the thing interactive, but we got to keep it moving. Thank you so much. Let's see our speaker again. And our next speaker. Which one's your talking? Sorry.
Yeah. All the way to the top. Here.
And our next speaker, my pleasure to invite academics, and she's going to tell us about the solar neighborhood.